miles, feet. But beneath the surface of things is another realm, 1 billion times smaller than we are. A dimension that holds the secrets to understanding our world. What makes steel strong? Why ice cream is delicious. What makes life possible? Secrets that help us create what we imagine.
The human creativity of chemistry, there's just nothing more beautiful than them.
This is the realm of chemistry, and these are its greatest discoveries. Philosophers believed there were just 4 elements: earth, air, fire, and water, and that air was the underlying element, a single substance responsible for the makeup of everything in the world. Centuries later, Leonardo da Vinci was among the first to suggest that instead of being an element, air might consist of 2 different gases. It remained a mystery until our first great discovery. England, the latter part of the 18th century. Clergyman and sometimes scientist Joseph Priestley conducted a series of experiments searching for new airs, what today we call gases.
So the thing about the 18th
Did this famous experiment, right?
That's exactly correct, and there are 2 things that go into that experiment. The one is mercury, this strange substance that's simultaneously a liquid and metal, and that's just crazy. I mean, whoever heard of a liquid metal? And so it was really puzzling. Priestley discovered oxygen, but Lavoisier invented it. So with Priestley's experimental work on gases, with the discovery of oxygen, with Lavoisier's articulation of a system of language, we have the whole conceptual scheme in which 19th century academic work is built, 20th century industrial innovation. We have pharmaceuticals, we have biotechnology, we have cell phones, we have plastics, that's exactly right. And all these things begin with the discovery of oxygen.
In the early 19th century, a British schoolteacher named John Dalton was hard-known elements such as oxygen, hydrogen, and carbon combined in definite and constant proportions. Atoms.
He used the word atoms. The idea of an atom, of course, goes back to Democritus.
Dalton developed what came to be known as his atomic theory, a revolutionary new system that defined the relationship between atoms and the elements to further unravel the mysteries of the atomic and molecular world, including our next great discovery. If these Lego bricks had existed in the early part of the 19th century, chemists could have used them to help illustrate something they were seeing in their experiments. A phenomenon that led... In 1869, a Russian chemistry professor named Dmitry Mendeleev was writing a textbook for his students when he began to wonder how he could best explain to them the 63 elements that were known at the time. To help formulate his thoughts, he constructed a card for each element. On each card, he wrote the name of the element, its atomic weight.
It is our icon. I mean, it's what we associate with chemistry. You go into any chemistry room, you see it.
Why is the periodic table of elements significant? It forever changed the way that everyone would learn and understand the elements. The periodic table of elements is to chemistry as notes of music are to a Beethoven sonata. Electricity was all the rage. People were busy making batteries and connecting them to just about anything to see the reaction. Electricity was like a new kind of fire. One of the great battery junkies of the day was Humphrey Davy, a self-taught English chemist. In 1807, Davy was performing a battery experiment in his lab. He melted some potash, a mineral found in the ground that also forms in the ashes of wood. Chemists had speculated that potash was a compound of several elements, but had not been able to prove. Davy had discovered the power of electricity to react with chemicals and transform them. Eventually, electrochemistry led to the rise of the aluminum industry, the production of semiconductors, solar panels, LED displays, even rechargeable lithium batteries. More importantly, she determined that the mysterious form of energy which enabled radioactivity to penetrate other materials was not the result of a chemical process, but seemed to be the interest of physicist Ernest Rutherford, whom we already met in the discovery of the electron. Rutherford found that radioactive material goes through a natural process of decay. As it moves through the process, the radioactivity spontaneously emits unstable and highly charged energy particles with the power to penetrate matter. Rutherford called them alpha and beta particles and gamma rays. Since those discoveries, we've learned a lot about radioactivity, the dangers as well as the benefits. Radioactivity has given us medical imaging, a treatment for tumors, a method for calculating the age of the Earth, and a power source for our spacecraft to explore the solar system. In the 1860s, John Hyatt, a printer and amateur chemist in Albany, New York, made news when he discovered a way to exploit the long, stringy molecules of cellulose found naturally in plants and created the first plastic. 50 years later, Belgium-born chemist Leo Baekeland took the next step in the discovery process.
One of the great pioneers was Leo Baekeland, who made a polymer called bakelite. The usual thing, chance favoring the prepared mind. He was mixing things, but he knew how to explore them. He saw the interesting properties of this.
From two chemicals derived from coal, Baekeland discovered the world's first fully synthetic plastic. And the landscape of the 20th century was forever changed.
Of chemistry, there's just nothing more beautiful than them.
A gram of black powder costs $500, about 30 times the price of gold. Remarkably, it's a special kind of soot made of molecules called carbon nanotubes. Each nanotube is about 1/1,000,000th of a meter in diameter, thinner than a strand of DNA, yet filled with a world of promise that has a lot of people excited, including a scientist who helped discover them.